Okay, so from the last slide, basically I gave you the potential energy diagram and we answered some questions regarding it, whether it's exothermic, in other words, whether it absorbs or releases heat. But when we look at number 4, this was more of a stoichiometry approach, or answering a stoichiometry question, right? Changing the molar ratios and how much heat would be produced. That's really the short-term goal here. So let's just do some questions regarding it. So for instance, and these solutions are quite short, as you can see. Here are the solutions. So you should have read these over. I'm just going to go over them quite quickly. The first one says the standard heat of formation, HF, which I haven't talked about yet, but it gives you a value for it. For sulfur dioxide is negative 296.8 kilojoules per mole. That's the key. That is kilojoules per mole, kind of like molar mass, right? Grams per mole. Here, this is kilojoules per mole. Asks how many kilojoules of energy are given off when 25 grams of SO2 is produced from its elements. So, if you get this much heat per mole, the question is how much heat would you get per 25 grams? So the goal here is to convert this to moles and then use that conversion factor, right? Conversion factor to go to kilojoules. That's basically it. So here you start with what you're given, 25 gram. You move to mole. Here's the molar mass of SO2. That's where those numbers come from. And then you simply plop in the conversion factor. For every mole, you get negative 296.8 kilojoules. Do the calculation, round to the correct number of significant figures, and that's how much heat's produced per 25 gram of SO2. Moving along to the next one. So hopefully that makes sense. The next one will be the same thing. The heat of reaction for the combustion of 1 mole of ethanol is negative 9.50 times 10 to the 2 kilojoules. How much heat is produced when 11.5 grams of alcohol is burned. So this will be the same thing here. Okay. 11.5 grams. Here, this is the molar mass of C2H5OH. Here's your conversion. I didn't write it in scientific notation. A bit easier to write in the numerator without it, but same thing, and you get your heat. By the way, this is rounded to 2 significant figures. It's a bit cheeky, but I did kind of give this explicitly to 2 sig figs. So that's why we rounded to 2. So that was just an extension from question 4 here. Okay. This time you're given the weights in grams, and you have to move the moles first. So let's do this practice problem. The delta H for the complete combustion of 1 mole of propane is negative 2.22 times 10 to the 3 kilojoules. Calculate the heat of reaction for the combustion of 33.0 grams of propane. Okay, so like before, you're going to start with grams of propane, C3H8. Now you're going to move, so by the way, the goal is grams to mole to kilojoules. Okay? It's asking for heat. So the weight of propane is 44.09, that's a 0, grams per mole. We have another step where we're simply going to cancel off 1 mole of propane, and for that you get negative 2.22 times 10 to the 3 kilojoules, and that will equal your final answer. Okay, which will be in kilojoules, and I'll just write down an unrounded value here. Now when you round this one, I suppose we are to 1 sig fig here, which means we're going to round up to negative 2,000 kilojoules. Typically I won't give you questions to 1 sig fig, but that one is. So there we have it. Okay, that's basically combining stoichiometry with thermochemistry, and to calculate the heat of reaction for these particular combustion reactions or any type of reaction. So notice how this is a combustion reaction. So typically in the other chapters you were interested in just the products, right? But it's funny that there is a kilojoule. Of course, I mean our whole point of using combustion in a lot of around the world is to actually generate energy, okay, which is just a byproduct of combustion. So now let's change topics here. Let's discuss our final topic in thermochemistry, which will be enthalpies of formation. The goal of this, though, is to take a reaction like this, okay, and theoretically calculate how much heat would be produced without actually carrying out the reaction. Because I'm giving you conversions here, right? You would not be able to do this question if I didn't give you this amount of heat per mole, right? How do you know that's how much heat is produced per mole? Either you experimentally measure it, or is there something more subtle going on? Okay. Same with all of these. All of these values, I'm giving you the conversion factor, right? I'm giving you these. The question is, similar to how you, using the limiting reactant, can find the theoretical yield of a certain application or reaction, in this, is it possible to theoretically calculate how much heat's produced? And the answer is yes. And certainly it's founded on a massive, a ton of experimental data. But the experimental data is not per reaction, okay? So it's actually per the formation of a compound, okay? Or an element, or a molecule, okay? So what do we mean by this? Well, enthalpies of formation, here we go. Basically, it's the amount of heat measured in kilojoules per mole, that's lost or gained when 1 mole of a substance is formed from its elements. So let's say water, for instance. Water formed from its elements. If you can find out how much heat is produced here, heat or gained or lost, okay, that would be the heat or enthalpy of formation, okay? Kilojoule per mole, that's crucial here. And basically this is measurable. So there are very, very precise tables that are available. I've posted one to the website. So let me just pull it up and you'll see what it looks like. So here it is right here. You can see it has all the different values of the heat of formation of different molecules or elements sometimes. Okay, measured in kilojoules per mole. The second page you can ignore for now. We'll use this in the physics portion. So let's just get used to using this table. When you look at these questions over here, what is the heat of formation for following compounds? Liquid water, you reference the table. So if I was to reference the table for liquid water, looking under the H's, here it is right here. Okay, negative 285.8. The unit is listed at the top in kilojoules per mole. So it means to form water from its elements, it would release, to be exothermic, it would release 285.8 kilojoules. Okay, you look up each one of these, you're going to get these results. Okay, so it's crucial that you can actually reference the table properly. Be careful of states. So some of the molecules will be listed twice, however the state will be different, either solid, liquid, or gas. The numbers will change. So the point of this is because you can actually calculate, and this is a observed or proven fact, I guess you could say. It's survived the test of time, that delta H is equal to the sum of the heat of formation of the products minus the heat of formation of the reactants. This is the tool we need. To find delta H without conducting an experiment. In other words, this is a theoretical way of calculating delta H. So you can do this for any single reaction. You can go back in your notes, find some of the chemical reactions, and just calculate the theoretical amount of heat produced or absorbed in those reactions using this principle. And what the principle is, there's the formula, so you should highlight this in your notes. And if you look at this example, which hopefully you've looked through, I'm going to do some practice problems after this, but basically you're going to reference the value for HCl, reference the value for bromine. Okay, the coefficients, you will multiply these values because you have two of them. These are the products, right? It's products, the sum of the products, okay, minus the sum of the reactants. So of course you're going to have to look up these guys as well. That's where all these brackets are coming involved here. Okay, these brackets, because you're doing that first and then you're doing this second to get your answer. So if I was to do a practice problem with you, our last slide, this is actually the last question in chemistry here. Calculate delta H for the synthesis reaction between ammonia gas and gaseous hydrochloric acid to create solid ammonium chloride. So if you write down the formula, it's actually kind of cool what we're doing here, because you're given this formula. If I was to give you the weights of ammonia and hydrochloric acid, you would be able to find the theoretical yield of this. Okay, but given nothing per mole, you can actually figure out how much heat would be produced. So there's lots that you can do in theory in chemistry. And here we go. Okay, sum of the products minus the sum of the reactants. We're talking about heat of formation, of course. Sorry, HF. So here we go. So here's the product. So we're looking up ammonium chloride first. You look up ammonium chloride. Here it is right here, solid, negative 314.4. So we have negative 314.4. I'm just going to put this in square brackets here. Okay. It's subtracted by, I'll put another square brackets, the sum of the reactants. So ammonia in the gaseous form, NH3, negative 46.1. So we have negative 46.1 plus hydrochloric acid, gaseous form. We'll find it down here, negative 92.3. Negative 92.3. Notice how I use parentheses here. I'm trying to show that you're summing the reactants here. So you just compute this and that's it. So negative 314.4 minus, if you have a display calculator or a Texas Instrument, you're going to press brackets here, negative 46.1 minus 92.3. This comes out to be negative 176. Okay, 0.0. Remember, we're adding and subtracting, so we're taking decimal places here, which is to 1 decimal place. And the unit is kilojoules. Okay, the unit is kilojoules. The reason it's in kilojoules, and perhaps this is not the greatest example, is because in this, I'm just going to point out in a different color here to wrap up, is that the coefficients 1 are in front. Okay, these coefficients are actually being placed into this equation. I'm going to rewrite it so you can see. You're actually going 1 mole times 314.4 kilojoules per mole, okay, minus 1 mole times negative 46.1 kilojoules per mole plus 1 mole. These 1 moles are coming from here. So if there's a 2, you have to multiply it by 2. Negative 92.3 kilojoules per mole. Running out of space. Hopefully you can see that. Notice how the moles will all cancel. Okay, and then you're going to be left with your result of negative 176.0 kilojoules. Okay, so that's important to keep in mind. So sorry for the long video. Not too many practice problems in this section, but hopefully the theory and the calculations make sense. So work on the practice problems and then move on to the physics portion.